Hello and welcome to another video in this series as we learn the basics of Lean to write simple maths proofs. We're in part 4 of our journey where we're looking at some more interesting kinds of proofs. In the last two videos we explored proof by contradiction and that was quite interesting. Today we're going to be looking at another significant milestone, which is induction proofs. It's a really powerful idea and it can really simplify some proofs, which would be quite a challenge otherwise to do. The idea itself I think is simple, but not everyone does, and that might be just how it's explained, so we'll have a go at doing that today as well. So let's dive in. So let's think about this task. The idea is for us to prove for every natural number n that 2 to the n is more than or equal to n plus 1. Now, intuitively, I guess that kind of makes sense. This is kind of a linear function. N plus 1 is a straight line if you plot it. And this is exponential. 2 squared, 2 cubed, 2 to the 4 grows very quickly. So we know it's true intuitively. But proving it isn't immediately obvious. And actually, all the tasks that we've done up to this point, they have been something we could probably do in our heads. That's been deliberate because we didn't want to do overly torturous mathematics. But the reason we've chosen something like this is to show that induction actually can crack what can look like a difficult task. So we don't have a problem believing this is true, but we just need to find a way of showing it. So we'll introduce this idea of induction. So the idea of induction, and there are different forms of induction, but this is what we're looking at today, is often called simple induction. The idea is that to prove a proposition P is true for any natural number, we need to show two things. A base case, so P is true for n equals 0. I'm pausing there because some of you will know induction and you'll know that actually you can start at a number greater than 0, but we'll keep it simple today. So we prove the base case that P is true for n equals 0. And then an inductive step, which is to prove an implication that if P is true for n, then it implies that P is true for n plus 1. We'll draw a picture actually because that's a lot of words. So if we've got a proposition and we haven't specified what it is, so it can be any proposition, about a natural number n, to prove it's true for all n, we need to do two things. 1, 2. The base case is to show that P is true for 0, and the inductive case is an implication. This wasn't actually clear to me when I was learning it, that if P is true for n, then it is also true for n plus 1. So as we said last time, or recently, to prove an implication A implies B, we assume A and see if we can conclude B. In some cases you don't actually need to assume A to conclude B, but that's fine. I'm mentioning that so it doesn't surprise you. But the idea is that we want to conclude this, and we may use this fact, and often in exercises you do. So what does that give us? Well, I'll just clear the screen there. What it gives us is, if we think of the natural numbers as a sequence like this, 0, 1, 2, 3, 4. If we can prove something is true for n, and the implication is that, if we can prove this implication, it means that if it's true for 1, then it's true for 2. If it's true for true, then it's true for 3. If it's true for 3, then it's true for 4. If it's true for 0, then it's true for 1. But that's not the same as actually proving it's true for any n. All we've done here is prove the implication. If it's true for one of these, then it's true for the next one. So we need a way to start this chain reaction. And often the base case is actually possible to prove, like, you know, the algebra kind of really collapses, or the logic is kind of trivial, just because 0 is 0. So sometimes it's easy to prove P0, which means we're given this. So if we're given this, then we can use this to say P1 is true, which means that P2 is true, and so on and so on. So that's visually what the idea of induction is. And there's a picture here just to illustrate that. So we need two things. This implication, which is the chain, but we need to start the chain with P0, the base case. And you can see why in other kinds of variations of induction, you might start at 2 or 3 because it doesn't work for 0 and 1, for example. But we'll keep it simple today. So how do we solve this thing here? Well, let's kind of work through it. I have written it down in the slides, and that's a lot of content on a slide. It's there for you to read in your own time. There's a blog as well if you want to read the blog at your own kind of pace. But let's do it by hand. So we want to prove that for all natural numbers n, that 2 to the n is more than or equal to n plus 1. And if we just drew a picture in case you weren't convinced, so n, and if you plotted n plus 1, it would be something like that, crossing the axis at 1. And 2 to the n, well, what's 2 to the 0? 2 to the 0 is 1. 2 to the 1 is 2. So that's actually the same then. 2 to the 2 squared is 4. 2, 8, 16. So you can see that one grows really quickly. You might have noticed that between 0 and 1, if these were real numbers, then this quantity is actually less than this quantity, but we're only talking about natural numbers, so that doesn't happen. Just pointing that out. Anyway, back to the task. So our proposition is that 2 to the n is more than or equal to n plus 1. That's our proposition. And the base case is for n equals 0. We want to prove that P0 is 0. And for the inductive case, we want to prove that Pn implies Pn plus 1. That's the chain in that reaction. So how do we do this thing here? Well, P0 says that 2 to the 0 is more than or equal to 0 plus 1. That's a proposition. We just need to prove it's true. Well, is it true? Well, 2 to the 0 equals 1, which is actually more than or equal to 0 plus 1. So the left-hand side does equal the right-hand side, this and this. So the P0 is indeed true. So that's proven. That's done. This one is slightly more involved, but not impossible. Let's look at this one. So we're interested in Pn plus 1. So Pn plus 1 says 2 to the n plus 1 is more than or equal to n plus 1 plus 1. Remember that n is now n plus 1. How do we do that? Well, let's look at this one. 2 to the n plus 1 equals 2 times 2 to the n, and we're assuming Pn is true. That's called the inductive hypothesis. The inductive hypothesis. So Pn is true, and what is Pn? It says that 2 to the n is more than or equal to n plus 1. That's the inductive hypothesis. That's what we're assuming to be true, and we can make use of that because 2 to the n is more than n plus 1, and we've got 2 to the n here. So that is more than or equal to 2 times n plus 1. Do you see how that works? We've changed 2 to the n with n plus 1, and there's a more than or equal to because we've used the inductive hypothesis. And this, if we expand it out, is n plus 1 plus 1 plus n. Now it's almost what we need to prove here. This bit is useful and this bit is extra, but actually that's more than 0 because n is a natural number. So that is n plus 1 plus 1. So we've proven that 2n plus 2 to the power n plus 1 is indeed more than or equal to n plus 1 plus 1. So this Pn plus 1 is true. I just thought I'd kind of talk through that, pen and paper as it were, but we can, if you want to kind of read through that, you can. So just to check it's all there, the base case P naught is saying that 2 to the naught is more than or equal to 0 plus 1, and because 2 to the naught is 1, it is more than or equal to 1, so the base case is true. And the inductive step is an implication. To prove an implication, we assume the antecedent and prove the consequent. And the antecedent is called the inductive hypothesis or the induction hypothesis. So for the purposes of proving this, we assume it's true. So we've got 2 to the n plus 1 is 2 times 2 to the n, and because we're assuming Pn is true, we've got 2 to the n is more than or equal to n plus 1. That's Pn. This one I've just highlighted here is Pn. So 2 to the n appears here, so we've got this expression expanded out, and we can see there's a useful bit and an extra bit, and that's okay because we're trying to prove more than or equals, so that reduces nicely. It's not a difficult bit of algebra, but if it's the first time you've seen it, you might not be kind of thinking in that way. The exercise at the end will give you another chance to practice that. This little thing here, whenever you have induction problems, it's one of the kind of common things to try. So whenever you have 2 to the n plus 1, it's worth kind of breaking it down into something times 2 to the n, and often this is the induction hypothesis relates to that quantity. So a little tip for doing exercises. So we've proven P naught and Pn implies Pn plus 1. So by induction, Pn is true for all natural numbers. That's how you do an induction proof. So if we look back to our problem, that's quite neat, because if we didn't use induction, this might involve, I don't know, calculus or some other horrible thing. Whereas with induction, all we've used is just addition and multiplication. There's no calculus, there's nothing fancy to do. It did need a little bit more thinking and planning, but the actual meat of the proof didn't need anything sophisticated in terms of techniques. So it's always we always try and write it out in small steps because it takes us towards the lean proof. So we write out a proof objective, which is always a good thing to do. We've said there are two cases we need to prove. We need to prove the base case, P naught, and we need to prove the inductance step, which is this implication. This one was easy to do, and this one has a hypothesis. We assume to prove A implies B, we assume A and prove B. So that's the assuming the antecedent to prove the consequent. And this is slightly more clearly written out than my handwritten notes. You can see 2 to the n plus 1 is 2 times 2 to the n, which is more than or equal to 2 times n plus 1. Why? Because that's the induction hypothesis. 2 to the n is assumed to be more than or equal to n plus 1. There. Then we can expand that out, rearrange a little bit into the form we want, n plus 1 plus 1. And we can ignore that n because it's always going to be more than 0. So we've got this chain of inequalities, So we've finally proven that. So by induction we can say that proposition is true for all n. Let's do this in Lean, and as you can see looking at the code, there's some new structure here, so we'll kind of talk through that. So the proof header is, as you'd expect, we're declaring a variable, n as a natural number, got the proof objective, there's no other hypotheses. Our objective is a proposition that 2 to the n is more than or equal to n plus 1. And the rest of this is the structure of an induction proof, or a simple induction proof. We say induction n with, that means we're going to do induction on n. And the reason we say which variable is that some problems, some tasks, will have more than one variable, so we need to specify which one. And then you always have these two sections, a vertical bar, 0, and then this kind of right arrow, as it were, equals more than. And then we have another section, which is vertical bar, and that's successor, or n plus 1, successor of n. We're going to prove something about the proposition with n plus 1, or the successor of n. And the inductive hypothesis, which we can name, here is called IH, and that'll be created. We'll see that in a second. So these are the two parts of the proof, the base case and the inductive step. And you can see it's almost like a proof by cases, or a proof where you've got two goals, a conjunction. So instead of focusing dots, we've got these little kind of branch arms, as it were. So this structure is always going to be like this, so we don't need to worry about what each individual element means. We just fill in the bits. So let's move our cursor here, and we can see that the proof objective is 2 to the n is more than or equal to n plus 1. That's the overall proof goal. So if we move the cursor to the beginning of this line, we can see there's the base case that we need to prove, which is this one here, 2 to the 0 more than or equal to 0 plus 1, and it's even labelled it case 0. So how do we prove this? Well, that's actually quite easy. We can actually just resolve it by norm num. We don't need a calc section at all, so that's easy to do. Why is that easy to do? Because it's just an arithmetic calculation. 2 to the 0 is 1, more than or equal to 1, and norm num can resolve that. We could do it with the calc section, but there's no need. The next inductive step is this goal. And you can see n has been replaced by n plus 1. So 2 to the n plus 1 is more than or equal to n plus 1 plus 1. And we've got an inductive hypothesis now, the induction hypothesis, which is 2 to the n more than or equal to n plus 1. If I had changed this, say, call that g, that's what it'd be called. But calling it IH tells us that it's the induction hypothesis. So how do we do that? Well, I think we're going to need a calc section for this. So we want to prove something about 2 to the n plus 1, and that is 2 times 2 to the n, and that's algebra, so by ring, equals, now we're going to use the induction hypothesis I think here, so 2 times, we're going to say it's more than or equal to 2 times, let me put some spaces in there, and that's n plus 1. Why is that? We have to justify it by rewrite induction hypothesis. In fact, it's because it's an inequality, it's a rel. And if we expand that out, that's n plus 1 plus 1 plus n, and that's just simple algebra. And we only want some of that, so we can say that's greater than or equal to n plus 1 plus 1 by Can normnum do it? Does it know that n is more than... Yep, it does. Great. I'll just put in an extra space there so it looks nice. There we go. So that's actually proven the induction step that 2 to the n plus 1 is more than or equal to n plus 1 plus 1. And that completes our proof. Simple as that. So the thing to take away here is that the proof bits are nothing more than what we've already done. Norm nums and calc sections and, using inequalities perhaps, a bit of algebra. But the overall structure within which this induction proof sits is new to us, but it's not complicated. You can just copy and paste that bit, and that bit. And if you did a different problem, I would probably just copy and paste that and then fill in the different steps. So I hope that was interesting. I hope that was, for me, that's exciting, because I think induction is a really interesting method of proof. Again, for me, it took me a while to get it, but once you get it, it's actually simple and it's actually quite powerful. And as I hope I've kind of illustrated, this kind of task without induction might have been a little bit hairy with maybe calculus or something else, whereas with induction we're just doing simple addition and multiplication. So the easy exercise looks very similar to what we've got. Instead of 2 to the n, there's 3 to the n. So it shouldn't be that difficult to do. Should I? Yes, I'll draw some pictures just to get us going. I won't solve it, but I'll just talk through how we might do it. So always good to write out what we're trying to do. We're trying to prove that 3 to the n is more than or equal to n plus 1. And if we're going to do this by induction, we'll have a proposition that says 3 to the n is more than or equal to n plus 1. And if we want to do it by induction, we want to prove a base case, p0, and we also want to prove that pn implies pn plus 1. Let's do each one separately. P0 is a proposition which says 3 to the 0 is more than or equal to 0 plus 1, and that becomes 1. So 1 is indeed more than 1. So that should be easy to do. So I'm kind of doing it for you, but not writing the code. And this one is an implication. We prove A implies B, which means we assume A as the induction hypothesis and prove B. So what is it that we can assume? We can assume that 3 to the n is more than or equal to n plus 1. That's the induction hypothesis. And we want to prove that this proposition, pn plus 1 is true. What does that look like? That says 3 to the n plus 1 is more than or equal to n plus 1 plus 1. So how do we do that? Let's take some space up here. So 3 to the n plus 1 equals 3 times 3 to the n. It's very similar to the other one, isn't it? And we can then use the induction hypothesis. 3 to the n is more than or equal to n plus 1. So that is 3 times n plus 1. And if we write that out, or expand it out, that gives us n plus 1, which is what we want, plus 1, which is what we want, and then we've got some extra bits, 2n and plus 1, I think it is, isn't it? So we've got 3 n's and 3 1's, and the bit we want is this bit, and this bit we can say is more than or equal to 0, because n is natural number, so we can then say greater than or equal to n plus 1 plus 1, and therefore pn plus 1 is true. So having proven the base case and the inductive step, we can say that pn is true for all n. So that's talking through it, but you'll have to code it. Any problems, let me know. If the idea of induction is causing problems, do say so and we'll have a conversation about that. I think this has been quite exciting. The idea of induction is quite powerful. When we started this journey, one of the things I was looking forward to was being able to do induction proofs in Lean. For me, it was kind of a milestone. Like, if we can do that, then we've got quite far. So if you've got this far, well done. You know, it's really, really good achievement. Next time, we're going to be looking at something related to induction called, well, we're going to be looking at recursively defined functions and proving something about them using induction. And you'll see that there's a strong link between recursion and induction. So that'll be quite interesting. See you next time. Bye.